Welcome to Science Aura. I am Dr. Sachi Vale. Today, we look at the sky, a realm once dominated by the roar of jet engines, now ruled by silence and invisibility. The B-21 radar represents the absolute pinnacle of aerodynamic engineering and stealth technology. But is this billion-dollar marvel already obsolete? We are entering an era where physics itself is weaponized against stealth. The concept of stealth is not about making an aircraft truly invisible to the naked eye. It is about manipulating electromagnetic waves. Traditional radar systems emit radio waves and listen for the echo. The B-21 radar is meticulously sculpted to scatter these waves away from the receiver. Its smooth, flying wing design lacks the sharp angles that usually reflect radar signals back. Beyond its shape, the B-21 is coated in highly classified radar-absorbent materials. These specialized composites act like a sponge for electromagnetic energy, converting incoming radar waves into minuscule amounts of heat rather than allowing them to bounce back. This combination of geometry and material science reduces the aircraft's radar cross-section to the size of a small insect. However, modern air defense systems do not rely solely on traditional radar. They employ a multi-layered approach, scanning various spectrums of energy. Infrared sensors, for instance, track the massive heat plumes generated by jet engines. To counter this, the B-21 radar features a revolutionary thermal management system designed to mask its infrared signature from thermal cameras. The engines of the B-21 are buried deep within its fuselage. The exhaust is mixed with ambient cold air before it ever leaves the aircraft. This drastically lowers the temperature of the exhaust plume, blending it seamlessly into the cold background of the high-altitude atmosphere. To a conventional infrared sensor, the bomber simply looks like another patch of cold, empty night sky. For decades, this combination of radar evasion and thermal masking has been the ultimate shield for strategic bombers. It forced adversaries to spend billions upgrading their traditional defense networks, often with limited success. The B-21 was designed to penetrate the most heavily defended airspace on Earth, deliver its payload, and vanish without triggering a single enemy alarm. But the landscape of modern warfare is shifting dramatically. The arms race has moved away from macroscopic engineering and entered the subatomic realm. We are no longer just fighting over the shape of an aircraft or the temperature of its exhaust. The new battlefield is defined by quantum mechanics, entropy, and the fundamental nature of information itself. This is the new threat. Enter the world of quantum sensors. Unlike traditional radar, which relies on bouncing macroscopic waves off a target, quantum sensors operate by observing the universe at the level of individual particles. They exploit the strange and counterintuitive properties of quantum physics, such as entanglement and superposition, to detect anomalies invisible to classical sensor technology. Imagine a sensor that does not need to wait for a radar echo. Instead, it measures the subtle disturbances in the electromagnetic field caused by the mere presence of an object. A quantum radar could theoretically generate pairs of entangled photons. One photon is sent out into the sky, while its entangled partner is kept inside the sensor. Whatever happens to one affects the other. If the outgoing photon strikes a stealth bomber, its quantum state is altered. By observing the retained twin photon, the radar system immediately knows that an object has been detected, regardless of how much radar-absorbent material the aircraft uses. The B-21's sleek geometry and advanced coatings are entirely useless against a system that relies on the fundamental laws of nature. The flying wing design of the B-21 radar is a masterpiece of aerodynamic efficiency. By eliminating the tail section and fuselage as distinct components, engineers have drastically reduced aerodynamic drag and structural weight. This design not only enhances the aircraft's range and payload capacity, but also removes vertical surfaces notorious for reflecting radar waves back to base. Every curve and contour of the B-21 is mathematically optimized using advanced computational fluid dynamics. Supercomputers ran millions of simulations to find the perfect balance between lift, stability, and radar evasion. The result is a shape that seems almost organic, lacking the harsh angles and flat surfaces found on conventional aircraft. It is a triumph of applied mathematics. However, flying wings are inherently unstable. Without a traditional tail to provide aerodynamic stability, the B-21 relies on a sophisticated fly-by-wire flight control system. Computers process thousands of sensor inputs per second, making microscopic adjustments to the control surfaces to keep the aircraft flying straight and level. The computers are the true pilots of this craft. This reliance on digital control systems means the B-21 is as much a flying computer network as it is a bomber. Its avionics architecture is designed to be fully upgradable, allowing it to integrate new weapons and sensors as they are developed. This open architecture approach is crucial for maintaining the aircraft's relevance in a rapidly evolving and hostile technological world. The structural integrity of the B-21 is another marvel of modern engineering. It utilizes advanced composite materials that are both incredibly strong and surprisingly lightweight. These composites are woven together at the molecular level, creating a resilient airframe capable of withstanding the immense stresses of high-altitude flight while maintaining its precise stealth contour. Maintaining this precise shape is critical. Even a slightly misaligned panel or a protruding rivet can significantly increase the aircraft's radar cross-section. Therefore, the manufacturing tolerances for the B-21 are extraordinarily tight. Every seam is sealed, and every surface is smoothed to microscopic perfection. The aircraft is treated with the care of an optical instrument. To protect its delicate stealth coating from the harsh elements, the B-21 requires specialized, climate-controlled hangars. Exposure to extreme temperatures, moisture, or even excessive ultraviolet radiation can degrade the radar-absorbent materials over time. This high level of maintenance ensures readiness, but also highlights the fragility of its physical stealth defense mechanisms. While the physical shape deflects radar waves, the radar-absorbent materials actively destroy them. These coatings contain microscopic particles of iron or carbon suspended in a polymer matrix. When an electromagnetic wave strikes the coating, it induces an alternating magnetic field within the particles. This process generates microscopic friction, converting the wave into pure heat. The exact composition of the B-21's coating is one of the most closely guarded secrets in the military. It is believed to be a broadband absorber capable of neutralizing a wide range of radar frequencies. Earlier stealth aircraft were optimized primarily for high-frequency targeting radars, but the B-21 is designed to be stealthy across the entire electromagnetic spectrum entirely. Despite these incredible advancements, physical stealth has its limits. Radar technology is not standing still. Adversaries are constantly upgrading their transmitters and receivers, increasing their power and sensitivity. They are developing networked radar arrays that can share data in real time, attempting to piece together the faint, scattered reflections into a coherent target. The thermal signature of an aircraft is just as critical as its radar cross-section. Jet engines burn fuel at thousands of degrees, creating a massive beacon of infrared energy. Heat-seeking missiles and advanced thermal cameras can detect this energy from miles away. The B-21 Raider employs a highly classified thermal management system to cool its exhaust and mask its intense heat. This system likely involves mixing the scorching engine exhaust with frigid ambient air from the stratosphere before it is expelled. The aircraft's internal ducting is designed to absorb and dissipate heat, preventing the external skin from warming up. By matching the temperature of its surroundings, the B-21 essentially becomes a thermal ghost, invisible to traditional infrared eyes. However, thermodynamics dictates that heat cannot be destroyed. It can only be transferred. The immense energy generated by the B-21's engines must go somewhere. While the exhaust is cooled, the aircraft still leaves a faint wake of disturbed air and microscopic thermal variations in its path. These subtle changes alter the entropy of the atmosphere, creating a distinct footprint. For decades, this faint thermal wake was considered impossible to detect against the chaotic background noise of the Earth's atmosphere. The sun constantly bathes the planet in infrared radiation, creating a blinding backdrop of thermal energy. Traditional sensors simply lack the sensitivity and computational power to isolate the B-21's microscopic thermal disturbance from this noise. This is the core philosophy of classical stealth: hide within the noise. If the signal generated by the aircraft is weaker than the ambient background energy, the aircraft remains undetected. The B-21 Raider is the ultimate expression of this philosophy, pushing the boundaries of material science and aerodynamics to ensure its signatures remain buried deep beneath the detection limit. But what happens when the enemy develops sensors that do not rely on traditional signal-to-noise ratios? What if they can analyze the fundamental nature of the light and heat particles themselves? This brings us to the cutting edge of modern physics and the greatest existential threat to the B-21 Raider, the advent of quantum sensing technologies and subatomic particle observation. To understand quantum sensors, we must first understand the photon. A photon is a fundamental particle of light and electromagnetic radiation. Both the radar waves bouncing off an aircraft and the infrared heat radiating from its engines are composed of photons. Classical sensors measure the macroscopic properties of these photon streams, such as their intensity or their wavelength. Quantum mechanics, however, reveals that photons possess intrinsic measurable properties at the subatomic level. These properties include polarization, momentum, and quantum spin. More importantly, photons can be entangled. Quantum entanglement is a phenomenon where two particles become inextricably linked, such that the state of one instantly influences the state of the other one. A quantum radar system exploits this phenomenon by generating pairs of entangled photons. One photon, known as the signal photon, is transmitted into the airspace. The other, the idler photon, is retained within the radar facility. The system continuously monitors the idler photon. Because of entanglement, any interaction the signal photon has will immediately alter the idler's state. If the signal photon travels through empty space, the idler photon remains undisturbed. But if the signal photon strikes the B-21 Raider, its quantum state changes. This change is instantly reflected in the idler photon. The radar system detects this alteration and registers a hit. Because this process relies on the fundamental connection, it bypasses traditional radar absorption. The implications of quantum radar are profound. It renders the physical shape of the B-21 irrelevant. It does not matter how smoothly the flying wing is designed or how perfectly the radar-absorbent materials are applied. The quantum radar is not looking for a bounced wave. It is detecting the collapse of a quantum state. This fundamentally changes the rules of engagement forever. Furthermore, quantum sensors are virtually impossible to jam. Traditional radar jamming involves flooding the enemy receiver with powerful radio noise, blinding their sensors. However, a quantum radar system is only looking for its specific entangled photon. Any external noise or jamming signals are simply ignored because they lack the unique quantum signature of the system's pair. This creates a terrifying scenario for stealth pilots. The very systems designed to protect them are rendered useless, and their traditional electronic warfare defenses are completely ineffective. The B-21 Raider, a marvel of classical physics, finds itself vulnerable to the bizarre and inescapable laws of quantum mechanics. The invisible shield of the American bomber is shattered. But quantum radar is not the only subatomic threat facing the B-21. Advancements in quantum infrared sensing are equally dangerous. As we discussed earlier, the B-21's thermal management system cools its exhaust to blend in with the atmospheric background. However, the engines still emit photons of infrared light, and these photons carry specific, unique quantum combustion traits. A conventional thermal camera simply measures the total amount of infrared energy hitting its lens. It cannot distinguish between a photon emitted by a jet engine and a photon emitted by the warm Earth or the sun. It relies on the engine being significantly hotter than the background. By cooling the exhaust, the B-21 successfully hides its thermal emissions within the natural noise. Quantum infrared sensors operate differently. They possess the sensitivity to analyze individual photons and measure their specific quantum states. Photons generated by the burning of aviation fuel have different statistical properties and quantum signatures compared to photons from natural thermal radiation. A quantum sensor can theoretically isolate the specific engine photons easily. This process is akin to finding a specific drop of water in the ocean, not by looking for its size, but by analyzing its molecular structure. The quantum sensor looks for the unique entropy footprint of the B-21's propulsion system. Even if the exhaust is cooled to match the ambient temperature, the quantum nature of the emitted light remains unchanged, providing a clear beacon. The challenge for adversarial nations is not just building these quantum sensors, but processing the unimaginable amount of data they generate. Monitoring the quantum states of billions of photons in real time requires immense computational power. This is where the development of quantum computing intersects with quantum sensing. A quantum computer processes this data instantly. By combining quantum sensors with quantum computers, air defense networks can run sophisticated algorithms designed to identify the microscopic entropy footprint of a stealth bomber. These algorithms utilize advanced machine learning to constantly refine their ability to distinguish artificial photon emissions from natural atmospheric radiation. The sky becomes a transparent ocean. This represents a monumental shift in the philosophy of warfare. We are moving from a paradigm of physical evasion to a paradigm of information control. The B-21 Raider was built to control its physical presence, minimizing its interaction with electromagnetic waves. But the future of combat relies on controlling the subatomic information your vehicle emits into the environment now. Sachi Vale here. As we delve deeper into this invisible war, it becomes clear that stealth is no longer a static achievement. It is a continuous, evolving process. The engineers behind the B-21 Raider are well aware of the looming quantum threat. While exact countermeasures remain classified, we can hypothesize about technological pathways to defend against subatomic detection. One potential defense mechanism involves quantum spoofing. If a quantum radar relies on detecting the altered state of an entangled photon, a highly advanced defense system might attempt to intercept the incoming signal photon, measure its state, and emit a perfectly identical decoy photon in its place. This would trick the radar system into believing no target was ever encountered. However, the laws of quantum mechanics make this incredibly difficult. The no-cloning theorem states that it is impossible to create an identical copy of an unknown quantum state. Any attempt to measure the incoming photon will inevitably alter its state, alerting the radar system to the presence of an interceptor. This fundamental law provides a robust layer of network security. Another theoretical approach is to manipulate the entropy footprint of the aircraft's emission. If quantum infrared sensors look for the specific statistical properties of engine photons, engineers might find ways to alter the combustion process or scramble the emitted light, making it indistinguishable from natural thermal radiation. This involves actively managing quantum states. This concept, known as quantum thermal masking, pushes the boundaries of current material science and thermodynamics. It would require materials capable of interacting with light at the single photon level, actively reshaping the quantum statistics of the emitted radiation. While currently in the realm of theoretical physics, such technologies could form the basis of future stealth. The development of the B-21 Raider is not just an aircraft acquisition program. It is a massive investment in the future of aerospace dominance. The military plans to procure at least 100 of these advanced bombers, creating a formidable fleet capable of projecting power globally. But the rapid advancement of quantum technologies threatens to undermine this immense investment. Adversarial nations are investing heavily in quantum research. They view quantum technologies as a critical asymmetric capability, a way to leapfrog traditional military advantages. The successful deployment of a robust quantum radar network would severely compromise the effectiveness of the B-21 fleet, shifting the global balance of power and neutralizing a key pillar of deterrence. This technological arms race is reminiscent of the Cold War, but instead of competing over nuclear yields or missile ranges, superpowers are racing to master the subatomic realm. The battleground is no longer just the physical airspace, it is the fundamental fabric of reality itself. The victor in this race will hold a decisive advantage, possessing the ability to see the unseen. Despite these daunting challenges, the B-21 Raider remains a technological marvel. It is important to remember that quantum sensors are still largely in the experimental phase. Building a functional prototype in a laboratory is vastly different from deploying a reliable, ruggedized sensor network across hostile territory. The B-21 will likely enjoy a long period of air supremacy. Furthermore, the B-21's open architecture allows for continuous upgrades. As quantum sensing technologies evolve, so too will the bomber's electronic warfare and stealth capabilities. The aircraft is designed to be a dynamic platform capable of integrating new countermeasures as they are developed. The cat-and-mouse game between stealth and detection will continue into the future. The integration of artificial intelligence plays a crucial role in the future of stealth. The B-21 is equipped with advanced AI systems that analyze threat data in real time. These systems autonomously adjust the flight path, optimize electronic warfare emissions, and manage the thermal signature to minimize the risk of detection by both classical and quantum sensors dynamically. As the bomber navigates contested airspace, its AI constantly evaluates the electromagnetic environment. It maps known radar installations and predicts the coverage of emerging quantum networks. By dynamically routing the aircraft through gaps in this sensory web, the AI maximizes the effectiveness of physical stealth features, keeping the B-21 completely hidden within the shadows. Another tactical advantage is the use of unmanned collaborative combat aircraft or loyal wingmen. The B-21 is designed to control a swarm of these advanced drones. These drones can fly ahead of the bomber, acting as decoys, electronic jammers, or even forward sensors. By flooding the airspace with multiple targets, the swarm can overwhelm both classical and quantum radar systems. Even a highly advanced quantum sensor has a limit to the amount of data it can process simultaneously. If the loyal wingmen emit sophisticated quantum noise or replicate the entropy footprint of the B-21, the enemy defense network could become saturated. This saturation tactic forces the adversary to waste valuable computational resources, analyzing decoys instead of the real bomber. This highlights the ultimate goal of the B-21 program: information dominance. It is not just about avoiding detection, it is about controlling what the enemy sees and understands. By manipulating the electromagnetic and subatomic data available to adversarial sensors, the B-21 creates a fog of war that prevents the enemy from making accurate tactical decisions in real-time combat. The physics of deception is becoming just as important as the physics of stealth. Engineers are studying how to manipulate the environment itself to hide the aircraft. This could involve using advanced lasers to create localized atmospheric disturbances that scatter incoming radar waves or alter the propagation of entangled photons, creating a temporary shield of chaotic energy. The future of the B-21's physical stealth may also rely on metamaterials. These are engineered structures with properties not found in nature. Metamaterials can be designed to bend electromagnetic waves around an object, effectively rendering it invisible to specific frequencies. If successfully integrated, metamaterials could provide an active cloaking capability for the B-21 aircraft. Unlike passive radar-absorbent materials, an active metamaterial's skin could dynamically adjust its properties based on the incoming threat. If illuminated by a specific radar frequency, the skin would instantly reconfigure its microscopic structure to perfectly guide the wave around the fuselage, leaving no echo and causing no state collapse for quantum sensors to detect at all. However, active cloaking and quantum countermeasures require immense amounts of electrical power. The B-21's engines are not just for propulsion, they are massive generators powering a city's worth of advanced electronics. Balancing the need for thrust, cooling, and electrical generation is one of the most significant engineering challenges in modern stealth aircraft design today. Every watt of electrical power generated produces heat, compounding the thermal management problem. The more advanced the electronic warfare and quantum countermeasures become, the more heat the aircraft generates, and the harder it becomes to hide its entropy footprint. It is a vicious cycle driven by the laws of thermodynamics, pushing engineers to the absolute limits of science. It is also crucial to acknowledge the current limitations of quantum radar. Generating and maintaining entangled photon pairs over vast distances through the chaotic atmosphere is incredibly difficult. Photons are easily absorbed or scattered by moisture, dust, and atmospheric turbulence. This phenomenon, known as quantum decoherence, destroys the entanglement very quickly. When decoherence occurs, the quantum radar loses its ability to detect the target. The signal photon simply becomes a regular particle of light, and the system reverts to the limitations of classical radar. Overcoming quantum decoherence in open-air environments is the single biggest hurdle preventing the immediate deployment of global quantum defense networks by adversarial forces. To combat decoherence, researchers are exploring microwave quantum illumination. Instead of using visible or infrared light photons, which are easily scattered, this technique uses entangled microwave photons. Microwaves pass through the atmosphere much more easily. While still highly experimental, this approach could significantly extend the effective range of quantum radar systems. Currently, the theoretical range of an open-air quantum radar is severely limited, often measured in mere tens of kilometers rather than the hundreds of kilometers required for strategic air defense. This means the B-21 radar can still operate with relative impunity at long standoff distances, using its advanced long-range precision munitions to strike targets from safety. The B-21 is not just a bomber, it is a long-range strike platform. It is designed to launch hypersonic missiles and advanced cruise missiles from well outside the reach of emerging quantum defense networks. By keeping its distance, the B-21 minimizes its exposure to subatomic detection while still delivering devastating firepower precisely where it is needed on the battlefield. The synergy between stealth bombers and hypersonic weapons represents the current pinnacle of offensive military strategy. While the B-21 uses extreme stealth to get within launch range undetected, the hypersonic missile uses extreme speed to defeat the final layers of enemy defense. This combination ensures that the B-21 remains a highly lethal asset despite quantum threats. Another factor preserving the B-21's dominance is the sheer economic cost of quantum technology. Building a single functional quantum radar prototype costs hundreds of millions of dollars. Deploying a nationwide network of these sensors, along with the cryogenic cooling systems and quantum computers required to run them, is an economic undertaking that few nations can afford to do. In many ways, the B-21 Raider is an instrument of economic warfare. Its very existence forces adversarial nations to divert massive amounts of capital away from other military programs and into highly experimental, unproven quantum research. Just as earlier stealth programs bankrupted adversaries trying to build conventional radar, the B-21 forces a costly quantum arms race. Despite the focus on advanced algorithms and subatomic physics, the human element remains central to the B-21's mission. The aircraft is optionally manned, meaning it can fly autonomously or with a human crew. The presence of human operators provides a level of tactical flexibility, intuition, and ethical decision-making that no artificial intelligence can currently replicate. In a highly complex electromagnetic environment where quantum sensors and AI algorithms are constantly trying to outsmart each other, human intuition can be the deciding factor. A skilled pilot can recognize subtle patterns in the threat data, anticipate enemy movements, and execute creative maneuvers that a purely logical machine learning algorithm might completely overlook. Beyond sensing, quantum physics also revolutionizes communication. The B-21 relies heavily on secure data links to coordinate with satellites, drones, and command centers. Traditional encryption can theoretically be broken by quantum computers. To counter this, the B-21 will likely utilize quantum cryptography, ensuring its communications remain absolutely unhackable by enemies. Quantum key distribution uses the principles of entanglement to create secure communication channels. If an adversary attempts to intercept the data stream, the act of observation alters the quantum state of the transmitted photons, instantly alerting the B-21 crew to the breach. This guarantees that the bomber's critical tactical data cannot be compromised or secretly monitored. This secure communication allows the B-21 to function as a central node in a vast, networked battlefield. It can process data from space-based sensors, naval assets, and ground forces, creating a comprehensive, real-time picture of the combat zone. The bomber is not just a weapons delivery platform. It is a flying command center orchestrating complex multi-domain operations. In this multi-domain environment, the threat of quantum detection is mitigated by overwhelming the adversary with coordinated attacks from all sides. While a quantum radar might briefly detect the B-21, the defense network is simultaneously blinded by cyber attacks, electronic jamming from drones, and kinetic strikes from naval vessels. Stealth becomes a cooperative effort. Cooperative stealth means the B-21 does not have to hide entirely on its own. It relies on the combined effects of the entire military force to degrade and confuse the enemy sensory network. Even if quantum physics makes perfect physical invisibility impossible, the strategic application of overwhelming coordinated force ensures the bomber can still successfully hit its target. Looking ahead, the evolution of the B-21 will heavily depend on breakthroughs in material science. Researchers are exploring topological insulators and quantum dot coatings that could radically alter how the aircraft's skin interacts with electromagnetic energy. These futuristic materials could provide active camouflage across multiple spectrums, including the visual and infrared. Topological insulators are materials that conduct electricity on their surface but act as insulators within their bulk. By applying these materials to the B-21, Engineers might create surfaces that perfectly absorb or seamlessly guide electromagnetic waves without generating detectable heat signatures. This could effectively neutralize advanced quantum infrared tracking system. The physics of the future will dictate the survival of the B-21 Raider. As our understanding of the universe deepens, the tools of warfare become increasingly abstract. We are transitioning from bending metal to bending the rules of quantum mechanics. The engineers designing the next generation of upgrades for the bomber must be as much theoretical physicists as aerodynamicists. These scientists are tasked with solving problems that seem to belong in science fiction. How do you hide an aircraft's entropy? How do you prevent a photon from collapsing its quantum state upon impact? The answers to these questions will define the aerospace dominance of the 21st century and determine whether the B-21 remains the apex predator of the sky or not. For now, the B-21 Raider stands as the most advanced, lethal, and survivable aircraft ever constructed. It is a testament to human ingenuity and the relentless pursuit of technological superiority. It has successfully mastered the classical laws of physics, rendering traditional defense networks obsolete and ensuring a credible strategic deterrent for decades to come. However, the clash between the classical stealth of the B-21 and the quantum vision of emerging sensors is inevitable. It is a fundamental conflict between two distinct eras of scientific understanding. The macroscopic world of aerodynamics and radar-absorbent materials is colliding head-on with the microscopic world of entangled particles and subatomic statistical probabilities. This conflict guarantees that the B-21 program will never truly be finished. The aircraft we see today is merely the baseline model. Throughout its operational lifespan, it will undergo continuous radical transformations. Its software will be rewritten, its skin will be recoated with new metamaterials, and its internal architecture will adapt to the shifting quantum landscape. The software rewrites will be particularly crucial. As quantum machine learning algorithms improve their ability to detect the bomber's entropy footprint, the B-21 SAI must simultaneously evolve its deceptive algorithms. It will be a silent, invisible cyber war fought in the skies, where lines of code determine survival just as much as the thickness of radar-absorbent materials. In this silent war, the margin for error is practically zero. A split-second delay in processing threat data or a minor miscalculation in thermal management could result in a catastrophic quantum state collapse detected by the enemy. The B-21 operates on the bleeding edge of physics, where the slightest imperfection is instantly magnified by the unforgiving laws of nature. Operating on the bleeding edge requires a fundamentally new approach to military engineering. The traditional development cycles taking decades are no longer viable. The threat landscape is evolving too rapidly. The B-21 program utilizes digital engineering and agile software development to ensure that updates and countermeasures can be deployed to the fleet in a matter of months. This agile approach ensures the B-21 remains a moving target, technologically speaking. By the time an adversary finalizes a quantum sensor capable of detecting the bomber's current entropy footprint, the aircraft will have already updated its algorithms and altered its signature. It is a perpetual race, demanding relentless innovation and massive ongoing financial investment. The financial burden of this perpetual race is staggering. Maintaining the stealth capabilities of the B-21 fleet against quantum threats will require billions of dollars in continuous research and development. It raises a critical strategic question. At what point does the cost of hiding an aircraft exceed the value of the strategic advantage it provides on the battlefield? For the foreseeable future, the strategic value of the B-21 remains absolute. The ability to project power globally, penetrate contested airspace, and hold any target at risk is the cornerstone of modern deterrence. The B-21 ensures that adversaries cannot hide behind impenetrable defensive shields, forcing them to constantly reassess their own vulnerabilities and strategies. This deterrence relies heavily on the psychological impact of the B-21. The mere knowledge that an invisible, highly lethal bomber could be loitering above is often enough to alter an adversary's behavior. Even if quantum radar eventually makes detection possible, the sheer complexity and uncertainty of the electromagnetic battle space heavily favor the stealthy attacker always. The psychological impact is amplified by the B-21's capability to carry both conventional and nuclear payload. It is a dual-capable platform, meaning any detected intrusion by the bomber carries the ultimate existential threat. This ambiguity forces defenders into a state of constant, high-stakes anxiety, further degrading their ability to make rational tactical decisions. As we approach the mid-century, the definition of stealth will have fundamentally changed. The B-21 Raider bridges the gap between the classical engineering triumphs of the past and the quantum informational warfare of the future. It is a transitional machine, representing the absolute peak of one scientific era, while desperately adapting to the dawn of an entirely new reality. This transitional nature makes the B-21 one of the most fascinating engineering projects in human history. It embodies our profound mastery over aerodynamics and materials while simultaneously highlighting our vulnerability to the deeper, stranger laws of the subatomic universe. It is a monument to human ambition, flying silently through a sky filled with invisible threats. The story of the B-21 Raider is a reminder that in science and warfare, there is no final victory. Every technological breakthrough inevitably spawns a counter-technology. The quest for perfect invisibility has led us to the startling realization that the universe is inherently observant. The very act of moving through the atmosphere leaves an indelible mark on reality itself. Whether the B-21 can successfully mask this indelible mark from the probing eyes of quantum sensors remains the ultimate question. The engineers are racing against time and physics to ensure the bomber retains its vital element of surprise. They are manipulating entropy, cooling exhaust plumes to the edge of possibility, and writing algorithms that rival human intelligence. Ultimately, the survival of stealth relies on acknowledging that the sky is no longer empty. It is a dense, interactive medium woven from electromagnetic fields and entangled subatomic particles. To fly undetected through this medium requires more than just a smooth shape. It requires a profound harmony with the fundamental forces of nature, a true mastery of the invisible. The B-21 Raider represents our best attempt at achieving this harmony. It is a dark, silent shadow slipping through a sea of radiation. As adversarial nations refine their quantum algorithms and deploy their entangled sensors, the shadow will be tested like never before. The outcome of this invisible war will shape the geopolitical landscape for the rest of the century entirely. We will continue to monitor the rapid developments in both stealth engineering and quantum sensing technologies. The intersection of these two fields provides a fascinating glimpse into the future of applied physics and the relentless nature of human conflict. The invisible battle space is expanding, and the rules of engagement are being rewritten at the subatomic level daily. The next time you look up at the night sky, remember that it is not simply an empty void. It is a complex, dynamic arena where the most advanced machines ever built are engaged in a high-stakes game of hide-and-seek, governed by laws of physics that we are only just beginning to understand. The silence of the sky hides a chaotic, invisible war of information and entropy. The B-21 Raider may be the pinnacle of aerodynamic stealth, but its true legacy will be how it forces us to adapt to the quantum era. It pushes the boundaries of what is possible, challenging us to rethink the very nature of observation, reality, and technological dominance. It is a masterpiece of classical engineering, soaring headfirst into a strange, subatomic storm. Thank you for exploring the incredible science behind the B-21 Raider and the quantum threats it faces. The universe is full of invisible wonders and terrifying technological advancements. Keep questioning, keep exploring, and never stop looking up. I am Dr. Sachi Vale, and this has been Science Aura. Stay curious, and we will see you in the next deep dive into the unknown.